Welcome back. This is lesson 4 of Machine Learning Zoomcamp session 6. And in this lesson, we will talk about decision tree learning algorithm. So in the previous lesson, we looked at training decision trees with sklearn. So we were able to train a tree. We experimented with one parameter already, max depth. And we saw if we let the tree grow indefinitely big, indefinitely deep, if we don't control the depth parameter, then it overfits. So we played a bit with this parameter. We've trained a decision stump, a tree with just one level, and trained a decision tree of depth 2. We'll look at this decision tree. So now let's see how a decision tree can actually come up with rules like that. So let's do that. So again, this is how a decision tree looks like. So we have a node. So this thing here, we call it a node with condition. So that's a condition node. And then inside this node, we have a condition. And this condition usually takes form. The form of this condition is some feature, and then it's larger than some threshold t. So there is a number, and it can be true, it can be false. If we talk about a simple decision stump, a decision tree with just one level, then we arrive at decision nodes. So here can be, let's say, OK or default. This is decision node. And it's often called leaf. So these are leaves of the tree. So this is where the tree doesn't go deeper. This is where we make a decision. To illustrate how the learning algorithm looks like, how it works, let's use a simple data set. So I already prepared a data set. Let me just take a look at this. Let me just copy it. Yeah, so this is how it looks like. So we have two columns here. The first column is assets, and the second column is the status. I'll call it data frame example. And let's turn this list into a data frame. Data frame data. Now, of course, we need to have proper column names. So columns, assets, and status. So this is how it looks like. So what we want to do now is we want to use this numerical column here, assets. So we want to train our decision tree using this assets column. So what we want to do is here, condition would be assets greater than some threshold t. And the question we have here is what is the best t? So what is the best split? And here, so this is called split. So we want to split the data set into two parts, and yeah, it will split it into a data set where the condition holds true. So let's say we have a decision tree here. So we have some data frame, and then we have the split assets greater than t. And then what we have is data frame, let's call it right. This is where this condition is true. So all the records for which asset is greater than t. And here we have data frame left. So here we have true and false. So this is called splitting. So we're splitting the data set into two parts where it's true and where it's false. So what we can do now is we can sort our data by the assets column. So sort values by assets. So here we see that for this data set, so we want to remember that we want to come up with a rule assets greater than t. So what are the possible t's? So t here is a threshold. So we can split our data set here, right? So t can be 2000, and we can split it here. So it can be 3000. Then we can split the data set here. And by splitting, so I mean that we just cut it here, and then it becomes our left part, and this becomes our right part. And then we can have a threshold of 4. If we split here, then 5, we can split. So here it's 5,000. Then here it's 8,000, and 9,000 doesn't make much sense because if we use this assets more than 9,000, there will be nothing on the right. So we don't need 9,000, and in the same way, we don't need a threshold of 0, because if we have this threshold of 0, then on the left there will be nothing. So these are potential thresholds that we can try. So let me just create a list that I'll call t's. So 2,000, 3,000, 4,000, 5,000, 8,000. So these are the potential thresholds. And what we want to do now is we want to cut. So for each of these t's, we want to cut our data set into left and right, and see which one is the best one. So we can move this, we can put it here, then we can put it here, 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 and this way we can just slide it down and see which split is the best one. So let's do that. So for t in t's, what we will do now, we'll now take our example, and then assets greater than t. So this will be our right data frame. So let's start with left actually. It's less or equals to t, and then right is this. And now we want to show this left and right. So for that, if we just do data frame left here and data frame right, we will not see them. Right? So we need to actually use a display function from IPython. IPython display import display. And the reason they don't show up because we are doing this in the loop, so they are not plus statement in a cell. So that's why Jupyter doesn't show them. Display left, display right, and then let's also print the t. So this is how each split looks like. So this is the split for, okay, I don't want to print t 2 times. So this is how the split looks like for 2000. I think we should have started with 0. Yeah, so here, because it's less or equals 2, that's why we have something on the left. This is what we have on the left. This is what we have on the right. So now we have a lot of splits across all these thresholds. So now we need to know which split is the best. For evaluating that, we have different evaluation criteria or split evaluation criteria. So we have our split. The split is assets greater than t. And we want to find the best one. Let's think how this could be used. So we have the split, which is assets greater than t. Then we split our data set into 2 parts, left and right. So this if it's true, and this is false. And just to make it easier, let's use an example. So I'll use an example with 4,000. So let's say t equals 4,000. So our left and right data sets look like that. So on the left, we have 3 default and 1 OK. And on the right, we have 1 default and 3 OKs. Let's say this is assets more than 4,000. So when it's true, what we will do here is we will predict OK, because the majority of people here, the majority of clients have the OK status. So prediction is OK here. And the same likewise in left. So we will predict default. And to understand how good our predictions are here, we can look at misclassification rate. So misclassification rate is when we predict everyone as default here, how many errors we make. What is the fraction of errors here? So here we have 3 default and 1 OK. So we predict everyone as default. So here, if we do this, we'll make 1 error out of 4. So our misclassification rate is 25%. So this is our left. And on the right, we have 3K and 1 default. So then we predict everyone as OK. And again, we have misclassification rate of 25%. So here misclassification rate is 25%, and here is also 25%. This is how we can evaluate the quality of our split. So for t equals 4,000, when we do this, we get a 25 error rate, misclassification rate on the left, 25 on the right, and then let's say we can take an average here. So average is 25%. We can say, okay, if we use this t 4,000 as the split, then the average misclassification rate we get is 25%. So we don't have to take average. So we can take a weighted average, for example. We have one example here and takes the examples here. Then it makes more sense to take a weighted average. So we will give this one more weight than this one. But here, for simplicity, we will just use the usual average. And of course, in real life, the way these algorithms work, they use a weighted average. So let's take an average. For the split of 4,000, the average misclassification rate is 25%. And yeah, actually, we can see this by doing value counts. So data frame left, status value counts. So we can see that here it says 1 out of 4 is misclassified. We can actually already normalize. It's true. And when we do this, we, instead of looking at absolute numbers, we look at ratios. So here 75% are default. So this is the majority class here. And then it means that for this OK people, for those who did not default, we make an error, and our error rate, misclassification rate, is 25%. And the same is here. So we predict everyone as default. So our misclassification rate is 25%. So let's actually do this now in the loop. So we have this loop here. And let's just execute that. To keep track of all the rates, let's just I'll just do a table. So what we want to do, we have this split, we have different T's, and then let's see a decision on the right. Then this misclassification rate, it's called impurity. This is just one way of measuring impurity. So we want our leaves here be as pure as possible. And misclassification rate tells us how impure they are. So there are other ways of measuring impurity. So here we use misclassification rate, but in general, this is called impurity. So let's call it impurity rate, then decision left. Let me just replace that. So here, decision left, impurity left, decision right, impurity right, and then let's also have average impurity table like that. So move it a little bit. So we start with threshold of 0. For threshold of 0 on the left we have default or decision. Impurity on the left is 0. So because this is a pretty pure split, so on the left, everyone is default and there is just one person. So impurity is 0. And then on the right, I think I have an error here, should be. So on the right, the majority class is OK. So we predict OK. And in this case, the misclassification rate will be 43%. So the next threshold is 2000. So for 2000, we again on the left predict default, and on the right we predict OK. And misclassification rate here for the left is again 0 because everyone is default here. And then for the right, misclassification rate is 33%. So 2 out of 6 are default, and we predict everyone is OK. So these are mistakes. So again, default 0, OK, 33%. So let's take a look at the next one. So the next one is 3000. So for this one, we split. So again, on the left, we have everyone is default. This is again a pure data set. And on the right, we have one default and the rest are OK. So then the misclassification rate here is 20%. So it's 3000 default 0, OK, 20%. So then let's do this for 4000. So I think we did this already on the previous slide. So we again have default and OK. And here the misclassification rate for both is 25%. So here we have one misclassified example, and on the right we also have one misclassified example. So 25% in each. Then the next threshold we have is 5000. So for 5000, we already have, like on the left, we have 50-50. So 3 out of 6 are misclassified, 50%. And then for the right, it's also, we have only 2 examples, but one of them is correct and one is not correct. So we again predict OK, 50%. And here, when it's 50-50, the decision whether to go with default or OK is a pretty arbitrary one. So I just went with here default and OK to stay consistent. But yeah, it can be default and default or OK and OK. Doesn't matter in this case because in both cases, the decision is pretty arbitrary. I think this is the last one, 8000, right? So let's again do default here. Yeah, and then we have 42 misclassification rate, well, actually 43, and then OK here, which is pretty pure, like it's just one record with 100% purity, so it's 0. So now let's calculate the average. So here it can be, let's go 21. Here is, I don't know, 16%. Here it's 10. Then 25-25, the average is 25. 50-50, the average is 50. And here we again have 21.5. And we see that this split split of 3000. So the reason is it's the best one because this 10% here is the lowest one. That's why it's the best one. Best T here is 3000 because impurity here is 10%. So this is how we find the best split if we just have one column. So what we do is we find all the possible thresholds like we did here. We sorted our data set and we looked at what are the all possible thresholds, and we selected all the distinct values except the last one, right? Because we always want to make sure that there is at least one record when we split. So we did that. And then for each of the thresholds, we split the data set and we calculate the impurity on the left and on the right. And then we computed the average impurity. And then from all the splits, we looked at the average impurity and selected the one with the best impurity, the lowest one, and it was 3000. So here we still make some mistakes, but this is the best possible split for this particular data set. Okay, and this way we learn a decision tree that looks like this. Assets greater than 3000, and then here we decide okay, and here we have default. So this is the tree we learned here. So we looked at how to do this with one feature. Let's see what happens when we have two features. So I'll add another feature now. Let's say we have a depth feature, which says how much depth the clients have. Let me just put some values here. So these have 1000 depth, this let's say have 500, and this person has 2000. So we have another feature. So this is how our data frame looks like now. We already tried the assets feature. So let's see what happens if we try to split by the depth feature. Where again, what we do is we sort values by that. See that the possible thresholds are here, so 500, then 1000, then we can split by 2000. Yeah, so it means that 500, 1000, and 2000. Just three possible thresholds that we can use to split this data set, because here we have a bunch of 1000. Right? So here it is 500, 1000, 2000, and we can do the same thing as we did previously, but let's try to also generalize it a bit. So previously we saw it for one feature, and the T's we have here, they are for assets. So let's just put them in a dictionary. Let's say thresholds, assets. For assets, these are the thresholds, and then for depth, the thresholds are this. And let's say if we have more features, then we can put thresholds for them here as well. And then what we do is we iterate over each of the pairs here for feature I'll call it T in threshold items. Then what we do is we basically do the same thing as here. We repeat the same, but not for assets, but for all the features. So here, instead of assets, we use feature. And we print this. So let me just also print the feature name. So just to separate them, print feature. Like that. Okay, so for assets, we already did this exercise. So this is exactly the same as we did. So let me just scroll this. And now we have that. And then there are multiple thresholds again. So let's copy this. I'll delete this one. Did this for assets already. Now let's do this for depth as well. For depth, we have three thresholds. So it's depth. First one is 500. For 500, so we predict OK and 0 impurity on the left. And then for the right, we predict default and it's 43% impurity. Next one is 1000. 1000. Then here the impurity for this for the left is 33%, and we predict OK. And then for the right, we impurity is 0%, and we predict default. And then we have the last one, 2000. We predict OK here on the left, and we predict default on the right, and impurity on the left is 43%, and impurity on the right is 0%. And then again, let's compute the average here. Let's say it's 21%. Here it's 16%, and here it's again 21%. So we see that for depth is not as useful for making the split as the assets, and still the best split here is actually this one. Right, so this one is the best one. Even if we try to use depth, we see that this one is still best. So then we decide that the best split is assets greater than 3000. This is how we do it for 2 features. For 3 features, it would be another group in the table, another bunch of rows with another variable that is doing the same thing. We can summarize this. So let's write this down, finding the best split. So what we do is for all the features we have, our example had 2 features, but if we had 3 or 4 features, we do this for every feature. So for F in features. And then for each feature, we find all the possible thresholds. Like for assets, we had like, I don't know, 6, 7 thresholds. For debt, we had 3 thresholds. So for each feature, we find the thresholds and we iterate for all the thresholds for this feature. So find all thresholds for F, and then we iterate over these thresholds for T in thresholds. So what we do here is we split data set using this feature greater than T threshold condition, and we compute the impurity of the split. So we do this for all the features, for all the thresholds, and then at the end, what we do is we select this condition with the lowest impurity. So this is what we do when we have multiple features. So for every feature, we select now, find all possible thresholds, we iterate over these thresholds, and then at the end, we find one single best split. We split this, and let's say we have our tree here. Let me copy it. So let's say we have a data frame here with 8 records. We split it into a data frame with 3 records and data frame with 5 records. And if we want, we can repeat this process. So we can split on the right, and we can split left. Of course, so when it's just 5 or 3, maybe it doesn't make sense to split. But let's say if we have 800 here and 300 here and 500 here, it makes sense to keep splitting. So we recursively apply this algorithm to the left and to the right, but at some point we need to stop. So previously, remember, we talked about if we let our tree grow indefinitely deep, then we risk overfitting to the data set. So here actually, here maybe it doesn't make sense to stop. Maybe it doesn't make sense to stop here. So we need to have some stopping criteria. Like we recursively apply this splitting, but how do we know where to stop? Then there are some criteria. Some stopping criteria that we can use for deciding if we should reiterate here one more time or it's time to stop. These criteria are, so the first one, group is already pure. So for example, for this one, this group is already pure. So it has 0% impurity. So all the records here are default ones. So here it doesn't make sense to split this group again. So because if we split, then here we'll predict default. And here we will predict default, right? It doesn't make sense here to split because all of these records are default anyways. So, but this one is not pure yet. So here we can keep splitting it. So group already pure. Then another thing we talked about this max depth parameter. So another stopping criteria is tree reach the depth limit. So if we already built 6 levels and our max depth is 6, we cannot keep going. We cannot keep growing the tree. And then the last one is here. Let's say we have only 5, right? So again, we're back to the case when it's not 800 and 300 and 500, but just 5. So this group is already too small. Suppose we don't want to split the group when it's just 5. So if it's more than 5, okay, we can split it. But if it's 5, we don't want to touch this anymore. So in this case, we can set the minimum size of the group, which we attempt to split. And then we stop when the group is too small. Group too small to split. Right. So if we see that the group is too small, and this is something we can control as well. If we see this is too small, we say, okay, here we stop and we make a decision, even though we know that maybe there is one. So in this case here, we had one default and the rest were okay. So if it's the case, okay, we still stop. So when we use this criteria, we force our model to be simpler, and this way we prevent it from overfitting. So with this, let's summarize the learning algorithm. So I'll call it decision tree learning algorithm. So first step is we find the best split. So this is what we described here. So we go over all features, we go over all the thresholds, and we find the best split. So find the best split. Then we check if the max depth stopping criteria is met. Stop if max depth is reached. Right? If it's not reached, then we check if the data set on the left is sufficiently large. So we don't want to keep splitting something very small. If left is sufficiently large, and if left is not pure yet. So if left is sufficiently large and not pure yet, what we do in this case, we repeat this on the left. So we execute the same algorithm, but for the data set after splitting. So whatever is on the left, we recursively do the same algorithm, and then we do the same for the right. So let me just copy it and replace this left with right. This is the learning algorithm for decision tree. Of course, it's more complex than that. So if you want to learn more about this, there is in scikit-learn, if you Google for scikit-learn decision tree and you go into this decision trees documentation, so they talk quite extensively about this model, how it works. And so there is one interesting thing here at the end, I think. Scroll it. Yeah, so these are the criteria. So this is what we call impurity here. What we used here is this misclassification rate as a way of measuring impurity, but there are other ones like entropy and Gini. And actually in practice, you use this, you don't really use misclassification, but I find it's easier to explain this learning algorithm using this example. But yeah, they are similar in a way that they say how pure a data set is, just using slightly different formulas. So here are the formulas, and if you're curious how it's working exactly, you can check it here. And as I mentioned, decision trees can also be used for solving regression problems. And they also explain how it actually works, so what kind of impurity criteria you can use for solving a regression problem. And actually, the impurity criteria in this case is mean squared error. So if you're interested in that, you can just go to this link and read more about this. Okay, and this is it for this lesson. So we covered a lot of things here, and this is actually the summary of this lesson. So this is how exactly we approach learning decision trees. So we will not implement this. This is just to give you an idea how it works internally. Yeah, so what we want to do in the next lesson is we can see that there are some parameters for the learning algorithm here. So this max depth is one of these parameters. Then here, like sufficiently large, how large is sufficiently large. So this is another parameter that we have. And what we will do in the next lesson is we will tune these parameters. So we will try to set different values for these parameters and see which one works best. So I'll see you in the next lesson.